Good morning, FS 201. We've finally reached Friday. I don't know how working from home and staying at home so much Friday is still so valuable to us, but it is. At least it is for me. So I hope you've been able to sustain these past few weeks and able to look at the day every day and find something positive that you are enjoying about the day because they do seem to be a bit long. Some announcements for FS 201. The packback submissions are due today by 11:59 p.m. So make sure you get that in today, Friday, April 10th. Quizam 12 opens today and is due next Wednesday, April 15th. And then Quizam 1, 2, 3. That should be 13. That's our last one. It opens Friday, April 17th, and is due on Wednesday, April 22nd, that last Wednesday of class that we have. So keep those in mind. What we've got left, Quizam 12 and 13, and packback submissions. Just remember your last packback submission is due on the last day of class. And then, of course, the final exam, which opens the last day of class and closes the following Wednesday on April 29th at 11:59 p.m. So, again, just like the Quizams, all online, 3 attempts, 6 hours. They build on each other. Each attempt does. So be sure that you're studying for that. Review those old Quizams. Look for things that still might be a bit confusing for you. If they are, go back to those old lectures for clarification. If it's still confusing, reach out. Let me or some of the TAs know, and we'll help you with those things. But do remember, please try to take that final exam early in the week or early in the time that it's available, so that if we have technical issues, we can work through those. So there will not be extensions on this final exam because there is so much time. It's open for so much time. All right. So you have questions, let me know. So on Wednesday, our lecture really centered around non-enzymatic browning. Maillard browning is what we finished up with. We talked about caramelization as well. So caramelization, we're just talking about sugars and heat. You need those two things to get caramelization. For Maillard browning, we need a bit more. We need these reducing sugars. Remember, that's almost any sugar except for sucrose that we're talking about in food. So reducing sugars that can form that open chain and have that double bonded oxygen at the top, and some kind of amine source, some kind of nitrogen source, which is typically protein in this case. So those amino acids and proteins react with the sugar and go through lots of different transformations. The optimum conditions for this to happen, for Maillard browning reactions to happen, intermediate water activity, a little bit of heat helps catalyze things along, but if you just give it plenty of time, this reaction will move forward. So the last thing we finished with was talking about glycosylation or just introducing non-enzymatic browning in people. So this is the first example, and excuse me, this is Maillard browning in your body. Right? So we talked about initially with carbohydrates that we didn't want that open ring structure for glucose. And this is one reason that we see polymers of glucose being formed in the body. It's much more efficient storage mechanism. And then we have less of those open ring structures. The reason we don't want that open ring structure in that carbohydrate is because it makes it more reactive. And it makes it more reactive in reactions like Maillard browning. So what happens in our bodies, this is often associated with diabetes and cataracts and things like that. So glycosylation happens. So we're adding this glucose on to the hemoglobin molecule, right? So our blood sugar, our glucose, is reacting with the proteins in our body. Now remember, structure equals function, right? So when the shape of these proteins change, you're basically inactivating them. They can't do what they're supposed to do anymore, right? So this is a big problem for patients that have diabetes, and this is one of the pathways where we start to see some negative health effects associated with these reactions. So the part of the body where we see, or one of the side effects of diabetes is that you have poor circulation in the periphery of your body. So in your hands and your feet and your extremities, right? Part of this is because that hemoglobin is having that glucose added on. It's being glycosylated in your body, and it can't do what it's supposed to do anymore. This also leads to kidney failure as your body tries to purify out this this compound that is not supposed to be there anymore. And sight loss is the last one. These glycosylations of proteins are a big problem with cataract formation. So all of these reactions are essentially Maillard-Browning reactions, a reaction of a reducing sugar glucose with proteins in our bodies. So Maillard-Browning is not just limited to foods. It does happen within your body. Another reaction that we do see that is related to Maillard-Browning is the use of sunless tanning lotion. If you are like me and really pale and you get out in the sun and you get very burned by the sun, but you still want to have a little color, that sunless tanning lotion is a great option. But here's how it works, which I think is really interesting. So there was a doctor that was working with kids who had issues absorbing proteins. And so she was using dihydroxyacetone in the treatment, and she noticed that when the children would get a little bit of this chemical on the skin around their mouths, the skin would turn brown, right? And so, being a good scientist, she observed this and she started experimenting on herself and applying this chemical to her skin, and found that indeed it did react and form this brown pigment, and that it was only reacting with the dead skin cells. So it's not reacting with the living cells underneath the skin, just that very surface layer of dead skin cells that's there. And so she was able to take that knowledge and transfer it into using products, making products for sunless tanning. So if you have a bottle of sunless tanning lotion in your home, take a look at it. You'll probably see this dihydroxyacetone listed on the active ingredient label. It doesn't cause any harm. There's no toxicity to it, but it is. You may notice here that we have this double bonded oxygen. So it is reacting with the proteins in your skin and initiating Maillard-Browning in your skin. So when you use that sunless tanning lotion, you're kind of toasting yourself, right? The same reaction that you would get when you toast in the morning, or you toast bread in the morning and get that nice brown crust on it. Right. So Maillard-Browning changes the color and the flavor, but does it change the nutritional value? And the answer is yes. And not only is it decreasing the calorie content of the sucrose, or not sucrose, of the reducing sugar that's there, it's also affecting the protein. So lysine is one of the main amino acids that is participating in the reaction of Maillard-Browning. It's one of the most reactive essential acids in Maillard-Browning, or that can participate in Maillard-Browning. It is essential. So it is an essential amino acid. Your body cannot make it. So when that reaction between the reducing sugar and the lysine happens, now the lysine isn't available for your body anymore. So this is a concern in certain products where you're looking at decreased lysine availability. This is dealing with redox potential, right? Reduction in oxidation. So of course, an antioxidant is going to participate in this reaction if it is there. This reaction does bind vitamin C, as vitamin C is an antioxidant, just like we learned about with enzymatic browning with polyphenol oxidase. Vitamin C does participate in this reaction. It can actually bind metal ions. This is not that great if you need those metal ions for your function of your body. And it decreases protein digestibility due to cross-linking. So your body is not able to break down these bonds that are formed during Maillard-Browning, and therefore it cannot break down and absorb the amino acids from that protein that you have consumed. So keep those things in mind. Typically, it doesn't shift the nutrition value enough to be of great concern for people that have a balanced diet and are getting enough caloric value. It might come more into play when you have somebody that has some nutritional challenges, right? And the last thing we're going to talk about with regards to Maillard-Browning is acrylamide formation. Now, this was really big in the news about 5 to 8 years ago, that acrylamide was being formed in foods that experience these very high temperatures that are common with Maillard Browning reactions. Specifically, acrylamide requires asparagine to be formed through the Maillard Browning reactions. Asparagine is an amino acid, and it happens to be an amino acid that's in higher concentration in potatoes. It is common in lots of proteins, but in potatoes, particularly the proteins that are there, have higher asparagine concentrations, right? So French fries is one of these things that forms a lot of acrylamide. Now, why are we concerned about acrylamide formation? Acrylamide is actually really bad for our health, and it tends to be like a heavy metal that once it gets into our body, it doesn't leave. So we're accumulating it our entire lives. Now, so very small doses of acrylamide throughout our life sum up to be larger dosages later in life. So if we could reduce the intake of acrylamide, because it is naturally occurring, if we can reduce that intake of acrylamide, then that's all the better, because then we're not accumulating as much of it. Acrylamide is a neurotoxin, so it can affect neurology within the body. It does have negative effects on fertility and is considered a possible carcinogen. So these are not things to take lightly. So we want to make sure that we're limiting the content of those. Things that do have a lot of Maillard Browning, like bread and coffee and potatoes, right, and French fries, these are all things that can have higher concentrations of acrylamide. But have no fear. At the company that is right up the road that Sonia Sue spoke to us, she works at Novozymes, and this is the company that has done a lot to invent or to create enzymes that can reduce acrylamide levels in things like French fries. I believe they have applied it to numerous other products like breads and coffee. So we're really just blocking one pathway of this Maillard Browning reaction to prevent acrylamide formation. It doesn't necessarily mean that we won't get the same flavors and aromas and color out of these products, okay? So this particular enzyme, acrylaway, actually reacts with the asparagine and changes it such that it's not available to participate in the Maillard Browning reaction anymore. So here in this reaction, we're looking at one of the reactants and altering those levels to prevent acrylamide formation. So this greatly reduces the acrylamide levels in French fries. All right, so that's all of our non-enzymatic and enzymatic browning lectures. And we had our information, and we've talked a lot about that, but with those reactions, a lot of what we were talking about is things that we see, right? The color formation, and that color formation of brown pigment, we have enough experience with food that we note that when we see that, it's going to give us a certain kind of aroma and a certain kind of flavor and taste in a food. So we have those linked in our minds, right? The same can be said about many other properties that we see with our foods. I think the common saying is we eat with our eyes first. So if it doesn't look appealing visually, we're probably not going to consume it, right? And this has a lot to do with the color of a food, the reflectance of a food, those surface properties that cause that reflectance, and whether it makes it more or less appealing to us. And that's going to be our next topic of discussion. So when we think about what color something is, what we're really seeing with our eyes is this visible wavelength. Now, we talked about this with our microwave heating, right? Microwave wavelengths are down here, a bit longer. In this visible range, these are the colors that we can see. So what happens when a food or an object interacts with light? If we have our light source here, and here's our object, when that light interacts with the object, 3 different possibilities can happen. The molecules in the object can actually absorb that light energy, right, and move to a higher energy state. the light can be transmitted through an object to the detector, and the detector can be an instrument, or the detector can be our eyes, right? So this light can go right through there, right to our detector, or this object can block the light and it can be reflected off of the object. So three different things: absorbance by the compounds or molecules within the objects, transmittance through to a detector or our eyes, and then reflectance or bouncing back off the object for this light. So those are the three things. Let's look at them a little bit more. The first ones we'll look at is whether something is clear, translucent, or opaque. This tells us a lot of what we should expect. When you compare this glass of milk to this glass of apple juice, this oftentimes we will think of in our head as creamy, right? This is not going to be creamy, this apple juice. So keep that in mind, that it conveys, sometimes it can have textural conveyance. Now, why is this glass of milk opaque? This glass of apple cider is somewhat translucent, and then the apple juice is clear. What's happening here is related to something called the Tyndall effect. If you've ever been out in the woods, and I hope in these recent times you've been able to get outside more and be amongst the trees, it's a very calming place to be. So if you've ever been out in the woods and you've seen light beams coming through the trees like this, you can see a ray of sunshine coming through the trees. What's happening here, and this happens very often in the mornings and the evenings, what's happening is that particles in the air are reflecting this light. They're bouncing the light off in a different angle. And so you can actually see the sunlight here, right? This is called the Tyndall effect. And this happens to a great extent in milk, right? We have casein micelles in milk, and we also have, if it's not skim milk, we also have fat droplets. And both of these things will refract the light in a different angle and not allow it to be transmitted through. In this apple juice that's been clarified, the light is transmitted right through it, right? So we can see light on the other side. Here, the majority of the light is being scattered by the molecules that are there and the fat droplets that are there. So anything that is an emulsion is going to appear opaque because those fat droplets are always going to be scattering the light. In the case of this apple cider that's somewhat translucent, what's scattering the light here is actual cellular material from these apples. The apple juice has been clarified, so all of that cellular material has been pulled out, whereas the apple cider is more of a dispersion has more of that dispersed apple cellular material there, pectic substances. So those substances will refract the light and scatter it, just like the compounds in milk are doing. All right, so this has to do with, this is the process of whether something is clear, translucent, or opaque. Definitely impacts how we look at it. Now, the other aspect of that is how light is reflected off of a surface. So if we have a mirror and something very, very smooth, the angle of the light coming in and the angle of the light reflected are equal, right? So something that's very shiny, like this particular cucumber, is going to have the angle of incidence and the angle of reflection of that light the same. Now, when something is rough, the surface is rough, the light is scattered in all different angles, right? So the reflection of the light is different angles from the incident. This gives us this matte kind of appearance, right? Now, even though the surface, when we look at these two things, might not look all that bumpy or all that smooth, it's really down on a much smaller level that these types of surface differences are really making a difference between whether this is shiny and this is not. So here, a typical cucumber that is grown does have a cuticle on the outside, a waxy coating, to help prevent absorption of things, fluid things, bacteria, evaporation of water from happening. And this is something that a lot of fruits and vegetables do on their own, is exude this coating of sort of a waxy lipid surface, right? Um, Now, this is what you might see in the grocery store, where this waxy surface has actually been enhanced. That the manufacturer or distributor of this product has put an additional waxy coat on there and almost polished the surface of the cucumber. It does help to extend the shelf life by reducing evaporation, but at the same time, it also makes it very shiny and appealing to the customer. All right, so that's how light is reflected on an object that is opaque or translucent. Let's think about colors and what we actually see when we're looking at that cucumber, that it's green. So if light is absorbed by a compound, if it's excited into a higher energy level, this is called absorbance. And then different absorbance patterns determine what we see with our eyes, right? So these are all the different visible wavelengths here. And this color block on the back is showing you these are the red wavelengths, these are the purple wavelengths, and we've got blues and greens, yellows and oranges all in the middle. Now, if we look at this, we're getting absorbance of these two different compounds here in this violet blue area, as well as reds and yellows. But reflectance, no absorbance here, in this green area. This is actually the absorbance spectrum for chlorophyll. So chlorophyll is the pigment that makes things green, like that cucumber. And this is what allows us to see. So if the pigment is absorbed, or if the wavelength is absorbed, then that pigment is not that color. It's where it's reflected. That wavelength is what we're going to see. So consequently, this reflection is happening here in this green region, and we see green, right? This is a picture of kale. So we see nice bright green colors here in this kale because that green wavelength is being reflected back to our eyes. All right, so let's think about pigments in foods. If you've been to the grocery store, especially the cereal aisle, you'll know that there are some really bright colors happening there. So there are 3 different categories of pigments considered by the FDA and what is acceptable in foods. Natural is the first category. So this is actually from a living organism. It doesn't have to be certified. And this happens a lot with juice concentrates. So some of the products in the market, say yogurts or actual juices, are using things like carrot juice extract or carrot juice concentrate that will turn their product a more orange color, right? Be a bright orange color. So sometimes when you see things like that on the label, they're there to actually give pigment more than flavor or texture. Okay, it's all about the color there. So these are some pictures of natural products that we see that can provide colors. Orange up here, this is carrots. So we've got some orange pigment, raspberries for red. Yellow here could be pineapple, green spinach. This bluish kind of color is red cabbage. So actually that pigment is anthocyanin, which we'll talk about in just a minute, and can be more of a blue pigment. And then a deep purple like blueberries or blackberries. So that's all natural pigments. Natural identical are the same compound that gives these items their color. So the beta carotene that makes a carrot orange is generated in a synthetic process, right? It's not purified from a living organism, but it's generated synthetically. So the compound is the same compound. It's definitely identical. These are exempt from certification. So it's just that they aren't coming from the original source. They're being synthetically manufactured. And then the last category is certified pigments. Now, these pigments are not identical to compounds that occur naturally. These are created compounds, right? And these are required to be certified by the FDA. From our food law section, you might remember there was a color amendment. So they are specifically addressed in that amendment. And an example of this would be FD&C Red number 40. And these are often used in things like candies and cereals and baked goods. You can see them here in this cake, the different layers, how bright and intense these colors are. This is pretty typical of certified colors, all right? So let's talk about those naturally occurring pigments and nature identical pigments that we saw on the previous slide. The first one is chlorophyll, and this is an example of a chlorophyll structure here. There are several different variations on this structure in nature, but in general, we've got this porphyrin ring here that is binding magnesium in its center. And then we've got this long chain of carbons that's attached. Now, this may look familiar to you, this long chain of carbons. This is very typical of a lipid type structure, right? So this tail is very hydrophobic. It doesn't like to be solubilized in water. So as long as this tail is attached, this isn't really a water-soluble compound. You might know that if you put green beans in water to boil, initially when you put them in there, the water doesn't turn green, right? If you take something like blueberries and mash them and disperse them in water, that water turns that purple-blue color almost instantly, right? So that should tell you that the compound in blueberries that gives that pigment is very water soluble, but the compound that makes green beans green isn't. And it isn't because of this phytol tail that is here on the end. So it does bind a magnesium compound naturally. And when you see green beans that are a bright green color, this magnesium compound is in the center. After you boiled green beans or you open a can of green beans that have experienced a lot of heat, that green is not quite as bright. It's more of an olive green. And it's because this magnesium has been released from the center of this porphyrin ring here, okay? Once that magnesium is released, that bright green color is no more. So managing this metal ion in the middle makes a difference. Now you can put other metal ions in the middle of this ring structure. Copper can be added or zinc can be added, and it does give a much brighter green tone to chlorophyll. It changes that pigment and the absorption spectrum of it. In fact, there was a process created called Very Green that once green beans were boiled or heated in some way, like in canned green beans or canned peas, if zinc was added to this process, that green color would still remain very bright and not the brown, olive brown tones, right? So this is a process that was approved by the FDA. I don't know how much it is used. I'm guessing not very much at this point, okay? So having that metal ion bound in the middle, naturally magnesium, is really important to getting the shade of green that we think of as being fresh. Now there's other metal-containing natural pigments. Myoglobin is a great example of this one, and it does shade our perception of the quality of meats. If you go to the store and you see a meat on the shelf that is sort of a purpley kind of color, you might not think that that meat is as high quality or as fresh as you would like, right? This has to do with oxygen binding to myoglobin. So this is the structure of myoglobin. You see it has lots of alpha helices in the secondary structure with some random portions as well. And in the center here, this is another ring structure, okay? In the center of this ring structure is an iron ion. And then iron ion is used to bind oxygen. So this is what stores oxygen in our muscles. And the amount of myoglobin you have varies with different types of meat. It's the reason that chicken breast are a lighter color compared to red meat. If you were to look at something like seal meat, in some very cold climates, seal is often eaten. And this is an animal that lives in the water and that does breathe oxygen, but that dives very deep for long periods of time. This meat is almost purple. It has so much myoglobin in it. And it's because this animal needs to store a lot of oxygen in its muscles because it's only getting it at certain times, limited availability, right? So if it stores more of it, it can dive deeper and be underwater longer. But it does change the color of the meat quite a bit, okay? but this color does vary with oxygen levels. So this is a good example here with different levels of oxygen. So whether that oxygen is bound to the iron or not in the middle of the myoglobin, right? So oxymyoglobin, looks like very fresh meat. This is what we're typically looking for higher quality. This is meat that's been exposed to oxygen and that myoglobin has bound the oxygen. This brown color is met myoglobin, right? And oftentimes if you see the brown color, you're thinking, oh, poor quality, right? It has to do with the amount of oxygen that is bound there. So if you get the chub packs of ground beef where it's the tube of ground beef with clips on the edge, oftentimes if you slice that tube open and look at the center, you're going to see something that's a little bit more brown than this outer portion that is bright pink. And this is because there's limited oxygen availability in the center of that chub pack. So maybe not necessarily correlated with poor quality, just the amount of oxygen that's available. So if you open that pack up and let that meat sit exposed to oxygen, the pigment may actually change as this oxygen uptake occurs, and it might move more towards this pink color. And then, of course, this purple color that you see sometimes, that's where we don't have any oxygen bound to the myoglobin. So those different pigments in meats are related to the amount of binding of oxygen by myoglobin. Another category of pigments is called anthocyanins. Anthocyanins are very, very common in the plant world. And as we stated before, they're very water soluble. So something like this purple cauliflower, a blood orange here, you see much higher in anthocyanin content than a typical navel orange. Red cabbage is a great source of anthocyanins. And then all of your berries, those are going to be related to anthocyanin content. Strawberries, which are coming in right now and delicious, are colored by anthocyanins. So what does an anthocyanin look like? There's lots of different types. This is a large category of pigments, and depending on the pH and its surrounding environment, it can change colors. So you see that we have lots of conjugated double bonds. That was something that we also saw, let me get back here real quick, in this chlorophyll compound too, right? Those conjugated double bonds where we have a single bond, double bond, single bond, double bond, all the way around. So in anthocyanins, we see those too, and these are typically ring structure compounds. And the pH, or the stability of this compound, as far as is it going to stay the same color, is very dependent on pH. So here we see pH 3, more acidic environments. pH 5 is about where you see red cabbage. That's the typical red cabbage pigment. And then as you move up, we get blues, greens, and then finally at this very high pH, pH 11, which is sort of unusual in foods, we see that same anthocyanin compound turning yellow, right? So if you take red cabbage here and simmer it, but you don't add any acid, right? You don't add some apple cider to it to give it some nice flavor or a squeeze of lemon juice, your red cabbage will actually start to turn blue because that pH is increasing as the acid is volatilized with boiling, right? So, so anthocyanins are very interesting in that they are very pH soluble. If you're at home and you want to try a neat experiment, boiling some red cabbage and getting that juice out of it, you can actually use it as a pH indicator, right? So anthocyanins can be a pH indicator. As you go up, you might change to blue and green if you add baking soda. If you add more lemon juice, you're probably going down more to this red pigment. So just something cool and interesting to see. Betalins is another group of compounds. This is a nitrogen-containing pigment that we see here. You see we've got a couple nitrogen ions in there, and we also have lots of conjugated double bonds, exactly what we would expect with a pigment. And up here on the top, what's this we see? This is a sugar compound, right? So this betalins are often glycosylated with sugars, meaning that a sugar has been added to this pigment compound chemically bound to it. All right, these are extremely stable to pH. They can be more neutral pH or more acidic. They're still going to be that reddish kind of color. But they're highly water soluble. If you've ever had to peel beets, you'll know that that pigment just solubilizes right off, right onto your hands, no problem. Very water soluble. But because it's so water soluble, it's pretty easy to wash off. And carotenoids are our last one. So when we start to see these red, orange, yellow colors that are very typical of things like pumpkins and sweet potatoes and carrots, these are all beta carotene. And remember, this is why Rennie used sweet potatoes in her noodles, right? Remember back to Rennie's noodles that she made to help people in natural disaster situations in her country Indonesia. Sweet potatoes were used because they were high in beta carotene, which our liver converts to vitamin A. So this is something really important for us to eat. So sweet potatoes are the highest, pumpkin has a little bit less, and then carrots are one of the lowest containing beta carotene levels. Now, these are not the only vegetables that are rich in beta carotene or carotenoids. Things like green vegetables are actually rich in beta carotene. So this kale that we saw earlier has the same amount of beta carotene as carrots. So the difference, the reason that the kale appears green and the carrots appear orange, the color of beta carotene, is that the chlorophyll is the dominant pigment in the kale, right? So if the chlorophyll starts to degrade, which we can kind of see here on the edges as this leaf gets older and past its prime, what you see is that beta carotene coming through. So don't think you have to eat just orange vegetables to get this, or orange fruits and vegetables. You can also get it from eating your leafy greens. Beta carotene and anthocyanins are some of the pigments that make up, that are shown in the leaves, just like in the fall. Just like the kale had the two pigments and one is dominating the other, in the fall, when the leaves begin to change, the chlorophyll begins to break down, and you can see these other pigments that are naturally present in the leaves, like the anthocyanins for the red leaves, and then the beta carotene or the carotenoids that are present in some of these yellow-orange leaves. All right, so the chlorophyll is actually just masking that beta carotene that is there. We have a few more pigment compounds that we're going to talk about here. And these are pigment extracts or non-certified colors. These are things that occur naturally. Titanium dioxide is one that you find very often in candies and cosmetic products. So this is actually just a mineral that is rock, so to speak, that is ground down to a powder and dispersed in food products. If you look at the label of M&Ms, titanium dioxide is actually on that label, but you don't have white M&Ms. The reason titanium dioxide is there, try biting one of those M&Ms in half and you'll see that the chocolate is coated with a little white layer. And that's a layer of titanium dioxide. And the reason it's there is to make the candy coating layer, the colored layer on the outside of the M&Ms, very bright and not diluted by the undertone of dark, right? So if we put something on a white background, its color shows up much better than if you have it on a dark type of background. That's why it's there. You can find it in toothpaste and sunscreen, right? We use it on sunscreen. The white sunscreen that can go on your nose has titanium dioxide in it because it actually, those little particles of ground powder in there refract the light away from your nose and prevent have actual physical barrier between your skin absorbing those UV rays. The second thing that I want to share with you is this cochineal extract. And this is actually called carmine very often. So this color, you can see a little bit of it here. This is actually a red color that comes from the insects that are living on this cactus. And they only live on this one particular cactus, but they are a very bright pinkish red kind of color. So once they're harvested and ground, they give you that pinkish red color. This one is often used in yogurt, so be on the lookout for that. And annatto is the last one. This is a seed of a plant here, and is very often used in Central American cooking. I went to Belize on a mission trip, and this annatto was used in making one of their traditional chicken dishes. They sell a paste at almost all the stores that is a combination of annatto and various spices that you dilute in water and rub on lots of different kinds of meat, but specifically chicken and Louise. Annatto is also something that you've probably eaten if you've eaten cheddar cheese. Cheddar cheese is not orange naturally, right? And here in America, we consider our cheddar cheese to be cheddar cheese if it's orange. In other places, the cheddar cheese is not orange, it's white. You can get those cheddars on the market here as well. The reason that cheddar cheese is orange in the US is because it is dyed with this annatto pigment. It's added into the cheese making process. And there's lots of different reasons that I've heard for this. One of them being that the seasonality of milk and pasture feeding cows affects the color of the cheese depending on season. So when cows would go out and eat grass from the pasture, that grass has a lot more carotenoids in it. Beta carotene as well, but carotenoids is a general class of compounds. Those carotenoids were conveyed in the milk from the cow and then made the cheese a bright yellow color. However, in the winter, when grass wasn't as available and those cows ate more grains or hay, that carotenoid content was lower in the milk, which made the cheese not quite as yellow. And people saw this variation in color with seasons, not as, oh, this is just what happens, but this is a quality defect. So the winter cheese was not as high quality as the summer cheese because the color was different. So someone came up with the thought of adding annatto in and making everything a uniform color so that you didn't get these seasonal variations. So that's one of the reasons I've heard for adding color into cheddar cheese. Another reason that I've also heard is to differentiate American cheddar cheese from, say, UK or Australian cheddar cheese as well. So we differentiate that cheese within the market and give it its own sort of branding and identity. So the last category of pigments are synthetic certified pigments. And those are the ones that have to be certified by the FDA. The FD&C here refers to the Food, Drug, and Cosmetic Act. And so they all have a common name, and then they have a number that's related to that FD&C Act. Lots of different colors ranging from blues, greens, reds, and yellows. Lots of different ones. So if you had a choice between a natural pigment and a synthetic pigment, why in the world would you ever choose a synthetic pigment? And there's lots of good reasons that people do, or manufacturers do. When you're using synthetic pigments, you need a very, very small amount because they're very, very concentrated. When a pigment is very concentrated, it has a high tinctorial powder strength, right? Tinctorial means the amount of pigment that's needed to color a certain volume of substance, right? Or the amount of color conveyed with a given amount of pigment. So it has a very high strength, very concentrated. It's also extremely stable. You'll remember how anthocyanins changed with pH. They could turn a totally different color. These synthetic pigments do not. They're stable to heat, to light, to different acidities, to oxygen exposure. Lots of different things that happen in the environment. If you were making a beverage to sell in, say, a convenience store, now think about how beverages are sold in a convenience store. They're sold in a glass front case, right? So they're exposed to light. If you happen to use a natural pigment like anthocyanins to make your beverage a nice pink color, then that light exposure could potentially turn that pigment to sort of a mucky brown color, right? In a very short period of time. And this would not be well received. Poor quality would be the message that it would be sending. So oftentimes synthetic pigments are used to overcome issues like that. Because they're so concentrated, they're also really low cost. And you're not worried about a natural disaster coming along and killing all of those carmine insects that are growing on the cactus leaves, right? So it takes a lot of the instability of certain markets out. And it's very consistent, it's very low cost. These pigments can also be modified such that they're very water soluble or insoluble. So if you want something to dye your new beverage that you're making a nice pink color, think about a dye. It's water soluble. Those that are not water soluble are called lakes. And you might wonder, well, why in the world would you need something that's not water soluble? It's coming up on Easter. So think about all the different candies that are out there. And a lot of those candies are chocolate candies. So if you're making a chocolate candy that has pink chocolate on it, that's a very low water system, right? Chocolate doesn't have much water in it at all. It's 1, 2, 3% at most. And so we don't need a pigment that can be dispersed in water. What we need is a pigment that can be dispersed as little bitty particles throughout the system and convey a color. And that's what lakes are. So lakes are water insoluble, and it's usually dried onto another substance, like an alumina type of substrate. They put the pigment on the outside of those particles. That color is then delivered by dispersing those particles within your system. And that's exactly how colored chocolates work. You can also take these synthetic pigments and make them into a variety of different forms to be used. Emulsion-based pigments, powders, liquids, paste. There's all kinds of applications, which is really important when you've got a variety of different products that you might use these pigments in. Having these different forms there is important. You can also do this with natural pigments. We talked a little bit about this with our caramel color there for making it into an emulsion that can be then dispersed in other emulsions or fat-based systems. All right, so that's the end of our lecture on what we see, whether the wavelengths are absorbed, reflected, whether the substance is clear, translucent, or opaque, colored, shiny, matte. There's lots of different variations on things that we see, and that all has to do with those three things that can happen when light is interacting with an object: absorbance, reflectance, or transmittance. We have different types of pigments. We have natural pigments that bind metals, natural pigments that have a variety of different colors based on their environments, particularly pH and heat. We can have extracts, non-certified pigments, and synthetic certified pigments. So keep in mind that these all range from natural sources, synthetically produced naturally occurring compounds, and then synthetically produced compounds that are not naturally occurring, right? So keep those things in mind. When you see a product on the shelf and you're reading the label, where's the color coming from? Is it naturally occurring, or has it been enhanced by some ingredients that have been added? It's important because color conveys quality to us. It can also even convey texture and flavor to us, right? If we see a candy and it's red, we're already thinking, oh, it's probably strawberry, maybe raspberry or cherry, right? Doesn't have to be just because it's red. Okay, well, it's Friday. I hope you guys have a tremendous weekend. Be sure to get outside, enjoy the sunlight, be with nature, stay away from people, but get outside, have some fun, do something interesting. Until next week.